Hi everyone, and welcome back to the 2019 PROS paper for Hardware Systems Application. In this video, we will be covering section B of the paper. I decided to split it into another video so that the previous video wouldn't get too long, and we can isolate this section of the paper here because it's quite a lot that we need to do. Okay? Alright, so before we look at the questions themselves, let's take a look at the instructions and how we approach this section of the paper. So we are presented with two case studies or two design options. Alright, they're labeled option 1 and option 2. And we are required to choose one of these situations and answer both questions 5 and 6 for 20 marks each. Question 5 requires us to draw an entity and state assumptions for the design of the system, and it further requires us to draw a state transition diagram. So we'd see some of the theory we learned about finite state machines coming into play here. Question 6 of section B is a full coding computer-based question, which is where we are required to write the code for the entity and the architecture of this design in Quartus 2, and we would be uploading our code files from this section for grading. Alright, so what we're going to do in this video is we will be looking at how to answer questions 5 and 6 for both of these options. So let's start with option 1. Alright, now in option 1, we see one of these traffic light questions which we have seen before. However, it's good to note that this question is one which comes a lot. You'd see it appearing in a lot of the past papers, but there are variations in these questions. Okay, so let's read the situation and see if we can make some sense of this. It says, on the crossing, there are 4 sensors, A, B, C, and D, which are being decoded into a signal that indicates the need for a change of direction. So what I'm going to do is I'm going to start underlining some of these keywords here. There is a signal, green for north-south, that indicates that the north-south light should become green, and a signal, green for east-west, which indicates that there should be a green for the east-west lights. All right? When we're talking about the north-south lights, we're talking about in this route. When we're talking about the east-west lights, we're talking across like this. Okay? These two signals, green for north-south and green for east-west, are provided as input into your design. You need to drive the lights. So one difference you'd see between this particular incarnation of the question versus the others is usually these questions are always based on sensor input for these 4 sensors. So we determine how the lights change and the signals that allow the lights to be to change from red to amber to green, etc., based on the input of the sensors. They do mention the sensors here. However, they are not giving us any conditions as to how the sensors affect the operation of the overall design. Instead, they are telling us that there are 2 signals, green for north-south and green for east-west, that are the inputs to this design. Okay, in other words, A, B, C, and D, our sensors, are no longer our inputs. So we can actually completely ignore this statement here because it has no bearing on our design. All right, we will be looking at questions where we have to decipher how the values of A, B, and C change and how they affect the operation. But for this particular question, we're only considering these two signals, green for north-south and green for east-west. Okay, let's see how the circuit operates now. It says the lights have green, amber orange, and red. In other words, a typical traffic light with these 3 sets of lights. They are in the amber or orange phase for 1 second. They are in the red plus amber orange for 2 seconds. There is also a phase where the lights in both directions are red, which is 3 seconds long. Assume the board you design for has a clock of 50 kilohertz. All right, so first of all, let's look at the different phases here. They are traffic lights, okay, and we know how traffic lights work, where we go from green to yellow or to orange to red. However, one of the problems that we would encounter with all of these traffic light questions is the fact that traffic lights in the UK and in Europe work a little bit differently. Okay, now if you've ever been to the UK or England, you know that when the lights are red and they are going to turn green for drivers to go, both the amber and red lights are on to indicate that the light is going to turn green. So it kind of signals you when you should start getting ready to pull off and stuff. So that is what is meant by this red plus amber orange phase for 2 seconds here. All right, so what happens is, let's assume that we have currently, let's say north-south green. Okay, if our north-south lights are green, that means that our east-west lights are red. All right, they can't both be green at the same time. So while the north-south lights are green and the east-west lights are red, what that means is that in order for the east-west lights to become green, the north-south lights must first become amber or orange. Let me just signify that with this yellowish line. These must become amber and orange. Then these will become red, because we know traffic lights go from green to orange to red. And now we are in some phase where both north-south and east-west lights are red. Then, as the east-west lights are going to turn green, they're going to become amber plus red plus orange, or red plus amber, like this. So there's a phase where east-west is red plus amber. Then east-west lights are going to become green. All right, and going back to from the transition from east-west green to north-south red, these lights would first turn orange, then they would turn red. Both lights will be red. Then we will have this red plus orange phase here. All right, and then we will have these lights going green. All right, and the reason we need to look at this is, in this design, in order to realize this design, we're splitting up the operation of this system into different phases. And we can think of these different phases as states, all right? And this is bearing on what we learned about finite state machines. So we have this overall system which accepts as inputs these two signals, green for north-south, green for east-west, okay? The system could exist in multiple states or phases. All right, so let's think about how this will operate, right? So first of all, they're telling us that the system is going to exist in different phases, which we're thinking of as states. Before we look at the question, which actually asks us to draw the finite state machine, let's just take a look at one more thing. They are telling us that the traffic light system is going to be transitioning through these phases, and they're going to exist in each of these phases for some particular amount of time. For example, 1 second, 2 seconds, 3 seconds. What is the significance of telling us that we are designing for a board which has a clock of 50 kilohertz? Well, the purpose of that is we would need to actually design a timer circuit, kind of like how we did 1 second timers using frequency dividers for our project. We would need to design a timer which will allow us to time for 1 second, 2 seconds, and 3 seconds. And of course, at the core of that timer, there will be a frequency divider. And the frequency that we are dividing to get that 1 hertz frequency for that 1 second timer is going to come from this 50 kilohertz clock that is on the board. It's much like how we design for a 1 second signal using a 15 megahertz clock from the Altera DE0 boards. All right, so that's the significance of this number, which means that we need to understand, or we need to be able to know how finite frequency dividers work. All right, just going to skip over option 2 for now to look at what the questions look like. So question 5, first of all, asks us to draw a block diagram of the full system showing its inputs, outputs, internal components, and their interconnections. State any assumptions made. So essentially, for 5 marks here, we would be required to draw the schematic corresponding to the entity. Okay. Part B requires us to draw a flow diagram or a state transition diagram. And of course, that state transition diagram would be based on the states that we're thinking of from this situation here. All right. So actually, what we could do is we could first draw this block diagram and get part A out of the way. Okay, so for your design, draw a block diagram of the full system that shows all inputs, outputs, internal components, and their interconnections. So let's see how we would approach this question. Right, so it tells us that the overall system only has 2 inputs, green for north-south, green for east-west. Yes, it lists these sensors A, B, C, D. However, because the question has not given us conditions for A, B, C, D for the lights to transition from green to red, and the fact that the question tells us that these signals, green for north-south, green for east-west, are explicitly our inputs, we are only going to consider those signals as our inputs. Additionally, we are going to be designing a sequential system because we're designing based on a finite state machine here. Because it's a sequential system and it tells us things like we have different times and we're using a clock of 50 kilohertz, that means that this system is also going to have a clock input and a reset input in order to initialize the system. So the block diagram for this, so let's start with question 5, part A. Okay, the block diagram is going to look something like this. We have our clock input. We have our signals green for north-south and green for east-west. Right, let me just increase the size of this and get some more space here. Right, that's better. Okay, so we have our clock here. We have a reset signal. We have signals green for north-south and an input signal green for east-west. Okay, the outputs of this, right? The outputs of this are now going to drive our traffic lights. Okay, so it says that the lights have green, amber, orange, and red in this line here. And it says that you need to drive the lights. So because we need to drive the lights, we would need signals for north-south green, north-south amber, north-south red, east-west green, east-west amber, east-west red. Okay, so we're gonna have, just go back to the diagram here. We are going to have a signal called north-south green for the green light for the north-south traffic lights. We're going to have north-south amber or orange. We're going to have north-south red. we're also going to have east-west green, amber, and red. All right, and that basically takes care of the block diagram. Okay, just remember again, the purpose of the reset statement, the reset signal, sorry, is so that the system can start in a known state on initialization or on startup. Okay. There's the next thing that we need to do is to state any assumptions made. So some of the assumptions for this particular question are going to look like this. Okay, so one of them will be assume that, actually instead of saying assume that, we know these are assumptions, so I'll just list them in point form. Okay, the circuit is, sorry, that is not very legible. So the circuit is rising edge triggered. In other words, we're gonna let the rising edge of the clock dictate the operation of the circuit. So the circuit is rising edge triggered. Another assumption is that we need to specify how our reset is going to work. So assume the reset is active high and asynchronous. All right, and we know what an active high asynchronous reset looks like, right? Assume that lights change state and this is just an assumption for this particular question based on green for east-west and north-south and not on sensor input A, B, C, or D. Right? In other words, we are no longer looking at permutations of A, B, C, and D to determine how our lights change state. Okay, so that's basically it for 5 marks there. Pretty straightforward, pretty easy 5 marks, assuming that we understand how the system works, right? The harder part of this question is the 15 marks part, which is the finite state machine. Okay, so let's try and figure out how this finite state machine is going to operate. So we know that, let's just list our states. Okay, so question 3, part B. So we have some states that this system is going to be in. Right? We have the north-south green state. And while the north-south lights are green, the east-west lights are going to be red. So that's going to be the name of that state. We are going to, during the transition from north-south green to east-west green, we know we're going to have to go into north-south orange state. Right, actually, so we have our north-south green state, our north-south orange state. We have this state where the north-south light is red, but at the same time, we know that east-west lights are going to be red as well. So north-south red, east-west red. So this is that state. Hold on, let me just finish writing this. So let's see the states that we have so far. We have a north-south green state, which is when north-south lights are green, right? In order to transition from north-south green to east-west green, this is going to be orange first, then this is going to be red. However, remember previously, the east-west direction was red. So before this turns green, both north-south and east-west are going to be red, sorry. So while they're both red, that's this phase that we're talking about here. There's also a phase where the lights in both directions are red, all right? Which is this phase that we just talked about here, all right? Now, moving from the state where both lights are red, we're going to have the east-west lights turning green after. In order for the east-west lights to turn green, there must be that state where both red and amber lights are on at the same time. And again, that's just a UK specific thing, right? So there's going to be a state called east-west red plus amber. Right? Then there's going to be my east-west green state. Right? There's also going to be an east-west orange state. Right? And there's going to be some state where in going from north-south east-west red to north-south green, that our north-south lights will be red plus orange. So I'm going to call that north-south red plus orange or amber. Okay? All right. So these are our states here. And we need to kind of understand how these states will transition from one to the other. Okay? So we could assume on initialization that the lights are in the north-south green state. So now I'm going to start. Actually, hold on. Before we look at that, what are the inputs to this system which will cause a transition? Well, we know that our signals green for east-west and green for north-south are going to cause transitions because that is what triggers each set of lights to become green, right? And then we're going to have as some input the time itself, right? Because we know that in some of these states, the only way to come out of these states is for 1 second to have elapsed, or for 2 seconds to have elapsed, or for 3 seconds to have passed by. Okay? All right. So what I'm going to do is I'm going to start the state diagram on another page, right? So remember how these state diagrams are drawn. We have these bubbles which represent the states, and these transitions which take us from one state to another, and along those transition arcs we are going to have the inputs into the system. Okay, and that is a very high-level example of how a finite state machine diagram is drawn. So each of the states that we talked about here is going to have its own state bubble. And we need to figure out how we transition from each of these states to the next in some sort of sequential order. Okay? All right. So let's just assume that we have, first of all, our north-south green state. All right. So I'm going to call that our north-south. Really hope we don't run out of space here. North-south green state. All right. And I am going to think of this as, let me just see if I can draw this a little neater. Yeah. I'm going to think of this as our initial state. Because it is our initial state, I'm going to put this dot with this arrow that's coming from nowhere, and the signal which allows us to come into this initial state is going to be our reset signal. So this is how we typically draw the first state of a finite state machine diagram. Okay. To denote our initial state, we have this dot with this arrow coming from nowhere, and it's usually the reset signal that allows the system to start in a particular state. All right. When we are in the north-south green state, when do we go into north-south orange? Well, to go into north-south orange, that means that the east-west lights want to turn green. So if those lights want to turn green, our signal green for east-west can go high, and that will trigger the north-south lights to go into the amber state and then the red state. So we're going to have this transition here for this state, and we're going to call the input into the north-south, into the system to transition states is going to be the green for east-west signal. In other words, when this signal goes high, we are going to change our state from north-south green to north-south, what did I call it? North-south orange. Okay. All right. Then it says that they are in the lights are in the amber orange phase for 1 second. So in other words, what that means is that for us to transition from north-south orange to north-south red, 1 second should have passed. Okay, so after 1 second, right, that's now the input to the system, and the reason it's the input to the system is because the clock signal is going to be triggering the timer, and that timer is what we use. After that time has elapsed, that's what we determine as the conditions for that transition. And when we go from north-south orange into the red state, we know that that is the state where both of my lights are red. We call that state north-south red, east-west red. Okay, so we have here north-south red, east-west red state. Right? We are in this state for 3 seconds. So that's this line here. There is also a phase where the lights in both directions are red, which is 3 seconds long. So when both lights are red, in order for east-west lights to turn green, we know that they have to transition to that east-west red plus orange or east-west red plus amber state. And we're going to stay in this state, this north-south east-west red state for 3 seconds. So after 3 seconds, I'm going to go into my, let me write the text first. This is where I'm going to go into my east-west, red plus, I'm going to change the name to orange since I had orange before. I know I wrote it down as amber, I'm just going to change it to orange, okay? So this is where I'm now going to have my east-west, red plus orange state here. All right. And what happens in this red plus orange state? Well, it says that the lights are in red plus amber / orange for 2 seconds, which means that in order for us to transition from east-west, red plus orange, to east-west, green, 2 seconds should have passed. All right, so now we're going to have this transition after 2 seconds to our east-west green state finally. All right. Okay. Now from east-west green, in order to transition from east-west green back to north-south green, I need to go through the same series of steps, but kind of in the reverse order. So in other words, my green for north-south signal needs to go high, which signals that the north-south lights are ready to go green. I'm then going to go into east-west orange, east-west plus, I'm going to repeat this state here, the east-west plus north-south red. Then I'm going to go into north-south red plus orange. And then from north-south red plus orange into north-south green. All right, so let's see how that is going to work now. Okay, so this transition is going to take place when green for north-south goes high. I am going to transition into my east-west orange state. Right? I'm going to stay in this orange state for 1 second. So I'm just going to bring this up here to kind of save some space. So after 1 second, I'm going to repeat this state here again. So we have to draw a separate state bubble for that here now. So that's also going to be, that's again the state where both of my lights are red. North-south red plus east-west red state. All right, we know that we always stay in that state for 3 seconds. So I'm just going to bring this down here again. Say after 3 seconds, we are going to be now in the north-south red plus orange, which is going to transition, which is going to signify that our north-south lights are going to be red plus orange, and then they're going to go directly into the green state. So here I'm going to have my north-south red plus orange. Right, and when we are in that red plus orange state, it always lasts for, according to the question, red plus orange for 2 seconds. So after 2 seconds, that's when I'm going to transition into my north-south green state and kind of finish the full diagram here. Right, so after 2 seconds, and that basically takes care of our state transition diagram. I know it's not very neat or tidy, but of course we are working with the limitations of Google Jamboard without a whiteboard. All right, this is the best we can do without a whiteboard right now. So one thing to note is that we just arbitrarily decided that we could start our system in the north-south green state. However, alternatively, I could have just as well said that my east-west green state was my initial state. And the only change, if I wanted to make east-west green my initial state, the only change I need to make is my reset signal could just as easily have started in my east-west green state like this. All right, and that is it for, actually no, that's not it. One minor thing we need to look at is how do we determine when this time has elapsed, the 1 second, the 2 seconds, the 3 seconds, etc. Well, if we think about it, we know that a timer to determine time is simply a counter plus a frequency divider. All right, we divide that frequency and we count the number of clock pulses that have elapsed, and depending on the number of clock pulses that have passed, we know that that will be the equivalent of 1 second, 2 seconds, 3 seconds, etc. However, while those clock signals from this 50 kilohertz signal are going to be high, they're going to be incrementing some counter. And the time that it takes for that counter, for that clock signal to increment to whatever is the frequency division number n, for 1 second, 2 seconds, and 3 seconds, we're going to have some counter, which is going to allow us to stay in each of these states here. All right, so that is going to look something like this. To determine when 3 seconds has passed, I still need to stay in this state while the counter is incrementing itself, and we can denote that by saying counter is equal to counter plus 1. Right? In other words, we are continuously adding 1 to counter. Right? Same goes for each of these states which stay on for a particular, each of these states which only transition after some amount of time, we need to have these counter states here. These counter inputs, sorry. Right? Now, this east-west green state and north-south green state don't need that, because those states transition based on the inputs green for north-south and green for east-west. Okay, so it's only my timed states like this that need these inputs here. And when we're looking at the VHDL code, we'll see where this counter comes into play. Right, again, here. All right, and this now is the end of our finite state machine diagram for 15 marks, right? Now, I know it's a lot to take in. I know that we haven't really looked at finite state machines in much depth, but the only way we're going to get this is by looking at the past papers, because they're pretty specific to the exams. So as we go through the situations for each of the past papers, we will look at how these finite state machine diagrams differ. Okay, of course, I will be uploading the official solutions to all of these exams on the course Moodle. All right. Okay, so let's see where we are right now in terms of the question. So yeah, we are finished with our finite state machine diagram. The next step is then to write the code for this. So to do that, let me actually open Quartus here. Right, and as you can see, this section of the paper is quite hefty, and this is why I always suggest that we reserve at least an hour for this part of the paper. All right. Okay, so we are now required to, let's see, design the system from section B, question 5. Of course, that system refers to the thing that's operating on this state machine, as well as the entity defined by this, with the aim to program it into an FPGA by using the appropriate software toolchain. Include comments in your code to explain the operation of your program. Each block of code should have a comments section explaining the purpose of that block of code. This is very important. Okay, we're going to see how we will be writing those comments in the code. All right. The same applies to important lines of code. So part A for 4 marks requires us to write code for the entity. Part B for 16 marks requires us to write code for the architecture for a total of 20 marks. And this is typically the format of the exam moving forward, okay, in terms of mark allocation. All right, so getting started with Quartus now. What I'll do is I'll create a new project, and I'm going to call this project Past Paper 2019, right? And the name of this project is going to be, the name of the entity is going to be traffic lights. Okay. All right, I have no pre-existing code file, so I can click on next. Before the exam, we're not actually going to program an FPGA board, right? So it does not matter exactly what we select here. I just like to select the board that we use just because, no particular reason, but you can also skip this step because it does not affect your solution or your answer. So you don't need to remember the model number of the board or anything like that, right? The question has not asked us for any simulations or test bench code either, so we don't really need to pay too much attention to what simulation tool we're doing. The point of this is just to get a text editor where we can type code and ensure that the code compiles. That is the most important thing. Our code needs to compile to ensure that it is syntactically correct. All right. All of the logic in the code will be determined by just looking at the code itself. All right. So let's first add a VHDL file to this file and to this project, and let's start typing. So I'm gonna type my package declaration here to get these things out of the way. Right, the numeric library allows me to get my integer numbers and my addition operations, which I will need for the counter. Okay, all right, so the first thing on the agenda is to write code to describe the entity. So our entity has 4 single-bit inputs, my clock, my reset, green for north, south, and green for east, west, and 6 single-bit outputs of type standard logic, north, south, green, amber, red, east, west, green, amber, red. So those are going to be our inputs and outputs. All right, so I'm going to call the entity traffic lights. So entity traffic lights is right. You see what I did there? I kind of just to ensure that I don't leave out any close brackets or semicolons or the end statements, I kind of type the surrounding code first, and then I'm going to fill in this stuff after. Okay, so I have my clock signal and my reset signal, which are both inputs of type standard underscore logic. I have my green for north-south and my green for east-west signals, which are also of type standard underscore logic. Of course, I could have just as easily declared all of these signals on the same line because they are all inputs of the same type, However, just to kind of differentiate my control signals from my data signals, I declare them on different lines, right? Finally, I have my outputs. So I have north-south green, north-south amber, north-south red, east-west green, east-west amber, and east-west red. And these are my outputs, also of type standard underscore logic. All right, and that takes care of our entity declaration there. Note that we are not talking about states just yet. All right, we need to write code to describe the finite state machine. And we know when we looked at writing code for a finite state machine that we have to declare a new type for the state, and all that stuff is done in the architecture. All right, all we are doing here is describing the entity and the outside black box of the system. Okay, and that basically takes care of this question part A for 4 marks. Pretty simple, pretty much a guaranteed 4 marks once you figure out what are your inputs and your outputs of your system. Okay, so let's now look at the architecture of this. So it's going to be a behavioral architecture because I'm going to be describing the state at a high level using this finite state machine. Okay, so my architecture behavioral of traffic lights, that's the name of my entity, is. So the first thing I'm going to do here is to define the states of the FSM, right? And we know that we define our states with the type keyword. So let's just take a look at the states that we have in this system here. So we have our states north-south green, north-south orange, north-south red, east-west red, east-west red plus amber, east-west green, east-west orange state, and north-south red plus amber. Okay, all right. So let's see. I'm going to use my type keyword here. I'm going to name the data type traffic light state is, and in brackets is where I'm going to list all of my states, right? Remember, the type keyword allows us to kind of create a new data type, and every signal or variable that we create of this new data type called traffic light state can assume one of these values that we are defining inside here. All right, so I have my north-south green state, my north-south amber or orange, whatever you want to call it, my north-south amber state, my north-south red east-west red state, my east-west green state, my east-west amber state, right? And to kind of, I can actually list these on different lines, right? As long as they have the brackets and the semicolon in the right place, right? Just to make it a little neater to read, right? So I have my north-south green, north-south amber, north-south plus east-west red, my east-west green, east-west amber. I'm gonna have that east-west red plus amber, and I'm gonna have that north-south red plus amber. All right, let me just put the underscore state here to kind of stick with the convention. So let's see. We had 1, 2, 3, 4, 5, 6, 7 states. Let's just make sure we have all of those states listed there. We have 1, 2, 3, 4, 5, 6, 7. My north-south green, north-south orange or amber, north-south red plus east-west red. I have east-west red plus amber, east-west green, east-west amber, and north-south red plus amber. All right, so that seems just about right. Okay. All right. The next thing that we need to do is, much like with any finite state machine code is to define signals, right? And notice that I'm writing these comments here because the question actually asks for comments, and the comments are gonna kind of help with you getting marks, because if something is wrong syntactically or if something is wrong logically, but your comments have the correct logic, you could still get quite a lot of marks, right? Okay, so we are going to define the signal for the counter / frequency divider, right? Actually, no, let us first define signals for current and next states for FSM. So I'm going to have signal, current state, and next state. These are of type traffic light state. Right? And that defines our state signals, right? And that's going to determine the transition to the next state, what state I'm currently in. It's going to help with our state transition logic, okay? All right, and we know that we need that counter to determine what the time that has passed so far. All right, so let's kind of take a look at what this counter is going to look like, right? So we know that we are operating with a 50 kilohertz clock. That's what the situation said above. All right, so if my input frequency is 50 kilohertz, right, which is 50,000, and the desired frequency that I have is 1 hertz, right? I know that the value that I need to count up till for 1 second is going to be 50,000. Sorry, let me just write the formula. It's going to be F in over F out. Which is simply 50,000. So when we were designing frequency dividers, we know that we would have had to develop this counter which would which would count up to 50,000, for example, and it would switch the state of the output signal from it would invert the output signal. But what's important to note is that we are not actually developing a separate frequency divider to control or to provide an output clock, right? We could actually take care of that frequency division logic inherently, in that we know that if we have some counter variable, and every time that, so we have something like signal count, right? This counter is going to be incremented on every rising edge of a clock, right? Now, based on these calculations above here, what that means is that every 50,000 rising edges of the clock signal, right, 1 second would have passed. So what that means is when count is equal to 50,000, 1 second has passed. When count is equal to 100,000, 2 seconds have passed. And when count is equal to 150,000, 3 seconds have passed. All right? I can actually use the same counting variable to keep track of these states. So in other words, I'm looking at when count is equal to 100,000, 2 seconds have passed. When count is equal to Okay, so if we know that we are going to be delaying through these states here for 1 second plus 3 seconds plus 2 seconds, then I could first look at when count is equal to 50,000. That means 1 second has passed, as this 1 second here. The value of count is now 50,000 here. To determine that 3 seconds have passed, another 150,000 clock cycles should have passed for 3 seconds. All right? In other words, count would have entered this state at the value of 50,000 that is continuously incrementing. So to determine that 3 seconds has passed, I have to look at 50,000 plus 150,000 to determine when 3 more seconds have passed. In other words, 4 seconds in total. That's 1 second plus 3 seconds is 4 seconds. And then I have to look to determine if 2 more seconds have passed, that's an additional 100,000 clock cycles have passed. So in other words, my counter, I'm going to be looking at it in different chunks or different phases of 50,000, 150,000, and 100,000 respectively. So the total value of my counter is going to count up to 300,000. Right? And this is for a total of 6 seconds. Right? And we'll see how this works. So what that means is that when I am declaring this signal count here, I can say signal counter is an integer and it has a range of 0 to 300,000. All right? And that takes care of the initial section of our architecture here. So now let's go on to the body of the architecture. Right? So we know that in finite state machine code, when we looked at finite state machines, we had multiple processes running concurrently. One of those processes determines the next state that I'm going to transition to, and the other state determines or takes care of the actual transition based on my clock edge. Okay? We know that multiple processes run concurrent to one another, and that is the most important thing to take away when writing code for this architecture. Okay? So we will need a process to take care of the state transitions. We will need a process to take care of actually storing the state and taking care of the transition. And we will need a state for the counter because our counting is going to take place in another state. And then finally, we're going to need a process for our output. So we're going to have 4 processes in this architecture. Each of these processes, again, reiterating, are running concurrent with respect to one another. Okay? They're all concurrent processes. So the first thing we should look at is the finite state machine process. And let's just get that out of the way. All right? And we are going to write the code for this finite state machine based on this diagram here. Okay? So we are assuming that our initial state is our north-south state, right? Let's just stick with that. So let me just put this back on our north-south state here. All right. So we're going to have the state transition process. Because I have multiple processes now, I need to actually name these processes so that I could probably keep track of them myself. Okay? This process is going to have a sensitivity list, and we need to try to understand what is this process sensitive to. Well, it is sensitive to changes in my input signals, green for east-west and green for north-south. It is going to be sensitive to changes in my counter because that is going to determine how many seconds have elapsed. And it is going to be sensitive to changes in my current state, like this. Okay, so that is all the signals that this process is going to be sensitive to. Now, when you're looking at the solutions for the past paper, you're going to see that the code looks a little bit different. And the reason for that is it seems as though they reuse some of the solutions for another question. So the solutions are a little bit wrong, okay? But that's okay. So the sensitivity list in the solutions is actually wrong. All right, so let's begin this process, and I'm going to put my end process keyword here one time so that I don't leave it out. All right. The first thing you would like to do for this process is to state that your next state is going to be assigned the value of your current state. And the purpose of this is if this or one of these signals causes this process to reawaken and there's no logic for the next state to transition, then we want to keep the next state as it is. In other words, we always want to store the value and tell the system, hey, the next state that you're going to be in is the current one, because you have to stay there. You're not moving to another state. All right, so that's always the purpose of this first line here. All right, and then as with any finite state machine process, we're going to have our case when statement. So in the case of my current state, right, when it's in north-south green, well, if green for east-west is equal to 1, then my next state is going to be my north-south amber state. Let's see if that makes sense. When I'm in the green state, and when I'm in the green state, if green for east-west goes high, I am going to transition, or my next state is going to be my north-south orange state. Right? So when I'm in north-south green, if this signal is high, then my next state is going to be my north-south amber state. I'm going to end off this if statement here. Right? I'm going to take care of the next state now. So what happens when I'm in this north-south amber state? Well, when I'm in the north-south amber state, in order to transition to the next process, I need to look at when 1 second has elapsed. In other words, I need to look at when the value of counter, which is being incremented in another process, is equal to some value that signifies that 1 second has elapsed. And when we were working this out here, we saw that for a 50 kilohertz clock, the elapsed time of 1 second corresponds to a value of count being equal to 50,000. Okay, so in other words, when I'm in the north-south amber state, if counter is equal to 50,000, in other words, if 1 second has elapsed, then my next state is going to be that, what is it called? It's called north-south red, east-west red. All right. In other words, I'm going to go from the orange light to the red light. Okay. What I could do is, let me just end off this architecture here so that I don't forget that, and I can save this code and actually compile to make sure that things are going good so far. All right, because this is going to be a very large piece of code which we don't want to have to debug with multiple errors at the end of it all. Okay. All right, so this is just stuff with the case statement for my default case and all that, which we'll take care of in a little while. So let me finish the code for this process and then we'll compile again. All right, so going back to the state machine now. from the north-south amber state, after 1 second has passed, we know that I'm going to go into the north-south red, east-west red state. What is the condition for me to transition from the next state, east-west plus orange? Right? So when I'm in this state, I need to look at when 3 seconds has elapsed. Okay? So when, in the case of when current state is equal to north-south red, east-west red state, I need to look at if 3 seconds has elapsed. Right? For 3 seconds passing, I know that that corresponds to a count value of 150,000. But I can't put 150,000 here because, yes, the individual value of 150,000 ticks of my clock corresponds to 3 seconds. But remember, the counter, when coming into the state, had a previous value of 50,000. So I need to look at its previous value plus the time it takes for 3 seconds to pass, which is equal to 200,000. In order to determine if 3 seconds has passed after the previous 1 second has elapsed, I need to monitor to see if my count value is equal to 200,000. Okay, and that is when we'll know if 3 seconds, in addition to this 1 second, has passed, then my next state is going to be my east-west red plus orange, or east-west red plus amber. Okay, so if counter is equal to 200,000, then my next state is going to be equal to east-west red plus amber. All right, so let's take care of the next state down the line now. So the next thing we're going to do is my east-west green state, because once my east-west lights are in the red plus orange, or once the red and orange lights are lit simultaneously, the next state is for those lights to turn green. All right, and when do they turn green? Well, they turn green after 2 seconds. So we're going to use the same logic here with this counter again. All right, so when I'm in the east-west red plus amber state, if my counter is equal to some value, then, and now we want to look to see if 2 seconds has elapsed. And this is, of course, in addition to the previous 4 seconds. So for me to get to this state now, my counter would have had to be at a value of 200,000. What is the individual count value that corresponds to 2 seconds? Well, it's count equal to 100,000. So I now need to look at my counter value being equal to 200,000 from before, its previous value, plus an additional 100,000, right, to determine if 2 more seconds have elapsed. So if count now is equal to 300,000, then the next state is going to be my east-west green state. All right, so the next state here is now my east-west green state. All right, so what's going to happen now? When I'm in east-west green, the input condition which causes a transition to the next state, which is the east-west amber state, is this input signal green for north-south going high. Kind of like how when I was in north-south green, east-west green going high was the condition for me to transition to north-south amber. Okay, so when I'm in the east-west green state, if green for north-south is equal to 1, then my next state is going to be equal to east-west orange or east-west amber. All right, what did we call it? We called it east-west amber state here. Okay, east-west amber state. Right? I think I forgot an endif above here. All right. When I'm in the east-west amber state, what happens? In my east-west amber state, I need to look for when 1 second has passed for me to go into the north-south east-west red state. Okay, so this is when my east-west lights are orange now, and I need to now look at when 1 second has passed. So much like before, I'm saying if counter is equal to 50,000, then, in other words, if 1 second has elapsed, my next state is going to be equal to my state where both of these lights are red. Alright, now you may be asking yourselves, how come we're checking the value of 50,000 here and not 350,000, right? But what we're doing here actually is we need to note that we limited the range of the counter for 0 to 300,000 just for us to time the 1 second, 3 seconds, and 2 seconds for one transition from one set of lights to the next. So because I limited this signal with this range, when I hit the value of 300,000, this integer signal is going to automatically reset at 0, all right? Which is why when I reach 300,000 here, counter is now equal to 0, and I can start back counting from 0 and look at when the value is equal to 50,000. Okay? All right. So now let's take care of, again, my north-south to east-west red. Sorry, I think I made one small mistake here. So we have a state where both lights are red for going from north-south to east-west. Right, so that's this one here, north-south to east-west, where both lights are red. But we are going to need a separate state going from east-west to north-south when both lights are red. So I'm going to call this east-west red to north-south red, just to make a distinction between the transition of going from north-south green to east-west green to east-west green to north-south green. All right, which means that this is an additional state here. All right, so I'm gonna list this here as a final state, east-west red to north-south red state. So it's important to note that we don't reuse that state there, all right? Because we wouldn't, if we reuse the state, we wouldn't be able to distinguish whether we're going from north-south green to east-west green or east-west green to north-south green when both of those lights turn red, all right? What that means is that I'm now going to have to add an additional state here. I'm going to call this east-west red, north-south red state, right? Which is what we're going to be dealing with here. All right, so if I'm going from east-west green to north-south green, and I reach that state where both of my lights are red, of course, for me to reach that state, I would have had to be in the amber state, and 1 second would have passed. Right? I'm in the amber state, 1 second has passed. I'm now going to go into this new state where both of my lights, north, south, and east-west, are red. However, this is the case where both of them are red, but I'm transitioning from east-west green to north-south green. So I'm going to call this state here now. Next state here is going to be east-west red plus north to north-south red. Right? When I'm in this east-west red to north-south red state, right? The reason I had to add in that extra state is I would have had another case when statement that would have been north-south red to east-west red, and the logic would have clashed. All right, so when I'm in this state, I want to check if 3 seconds has passed. So if my counter is equal to 200,000, then if 3 seconds has elapsed in addition to 1 second, then my next state is going to be equal to my north-south red plus orange. So this is now my north-south red plus amber. In other words, it's a state which tells the driver that the north-south lights are going to turn green, right? And again, that's just a UK specific thing. So when I am in my north-south red plus amber state, if my counter is equal to 300,000, again, because I need to wait until another 2 seconds has passed here, I'm going to say in addition to 4 seconds because I would have had 1 second passing here plus 3 seconds passing here, giving me 4 seconds in total. All right. Then, of course, my next state is going to be that north-south green state. All right, and that basically takes care of the finite state diagram, going back to this section of the diagram here, which is our initial state. The last thing to do is, as VHDL programming practice goes, for any case when statement, we need to have a default case. So I'll have something like when others, my next state is going to be equal to north-south green state. All right, and that's just my default case there. All right, let's compile this and see what happens here now. Okay, everything seems to be syntactically correct, which means that we can go on to the next process in this architecture here now. Okay, so this was my process. To determine the next state logic, that's what we refer to it as. And this here now is the process storing the current state and performing the transitions on clock edges. All right, so I'm going to call this one now my let me see, I have the state transition proc. I'm gonna call this, I don't know, we don't really need to, the naming doesn't need to be too stringent. I'm gonna call this traffic light state changer. Actually, let me just call it state changer. Right? It's a process which has a begin and end process keyword. And this now is going to be sensitive to changes in my clock and reset signals. All right, so we stated that we wanted the reset to be an active high asynchronous reset in our assumptions in part A. Right, we said that assume the reset is active high and asynchronous. So the first thing we're going to look at is the value of the reset signal. So if my reset is equal to 1, then what happens? Well, the purpose of the reset in this finite state machine-based system is to start in that initial state. So when my reset is 1, my current state is going to be the north-south green state. So if reset is equal to 1, current state is equal to north-south green state. Right? And then, because it was an asynchronous reset, it is not governed by the clock. So the next thing I'd want to do is now look at the rising edges of my clock. So I'm going to look at else if clock event and clock is equal to 1, then just put this end if statement here one time for this overall block of logic. And what's going to happen here? Well, on every rising clock edge, I just want to take care of the actual state transitions if there is a change in this other process above. All right, so my current state is going to be equal to my next state. All right, let's look at this a little bit. So in this process above here, we know that this signal next state is going to be determined based on some conditions. All right, these conditions are evaluated when this process is executed, and this process is executed based on some change in any of these signals here. On every rising clock edge thereafter, that's in this block here now, we are assigning the value of next state determined in this piece of logic here to our signal current state. If none of these conditions are satisfied, in other words, if there is no condition for a change, for example, if counter is equal to 10,000, I don't want to change the next state to the east-west state. I want to stay in this amber state. So for me to stay in this amber state, this line of code is going to be evaluated. It's going to say next state is equal to current state, because current state is still going to stay in north-south amber, for example. All right, this condition is not going to be satisfied, but next state will still have the value of what is going to be currently, so that when we come to this block of code here, next state, the variable, is storing the value of what it's going to stay at, and that corresponds to these transitions here. All right, and that value then gets pushed into this signal, which is going to allow me to stay into the current state. So that's the importance of this statement here. It allows me to stay in a state when some condition has not yet been satisfied. And that's quite important because we have these concurrent processes determining the state change and the next state logic. All right, so that takes care of the code for our finite state machine. And that's basically for the finite state machine. The only other thing we need to do now is to write a process for the counter, right? So this is going to be a process which is sensitive to the clock, yeah. Okay, and looking at the state transition diagram, when do we want to start counting? We want to start counting, that's this increment here, as soon as I enter this state. What is the condition for me to get to this state? Well, the condition for me to get to this state is when green for east-west is equal to high. Likewise, after I've reached 300,000 and I reset to 0, when do I want to start this counter counting again? Well, I'm only going to start this counter incrementing itself when green for north-south is equal to high. In other words, I'm going to have a condition here that says if the current state is equal to north-south green, or when the current state sorry, not this, is equal to east-west green, that is when I want to reset the counter, right? Note that this is an integer value, so there's not any quotations or anything around it, all right? Else, if, and here now, we're going to take care of a bunch of state transitions. All right, just one thing to note, which I left out. We kind of want to encapsulate this to take care on every rising edge of the clock. All right, so if this right, now here I'm going to determine when I would like to increment my count. Well, when do I want to increment my count? I want to increment my count when I'm in north-south orange, when I'm in north-south to east-west red, when I'm in east-west red plus amber, when I'm in east-west amber, when I'm in east-west to north-south red, and when I am in north-south red plus orange. So I have to look at when the current state is equal to this, if the current state is equal to this, or this, or this, or this, or this, that is when I would like to increment my counter. Okay, so I have to say if my current state, and I'm going to put each of these in brackets. Okay, so if my current state is equal to north-south amber state, or if my current state is equal to north-south red to east-west red state, or if my current state is equal to east-west red plus amber, and we're going to basically do this for all the states where we want to be counting. Right, so if I'm in north-south orange or amber, north-south to east-west red plus amber, east-west orange or east-west amber, or I'm in east-west red to north-south red, or I'm in north-south amber plus red. So that's going to be, what did I call it? North-south red plus amber. And that is when I would like to increment my count. So note how this if statement is stated. Each of the individual conditions is listed in a pair of brackets by itself, and I have this overall pair of brackets encompassing all of these statements together, and I want to look at when either of these signals or either of these conditions is true, all right? And that is going to be achieved using Boolean OR logic. So else if any of these conditions is true, then that is when I would like to increment my counter. All right. The only reason why we did this on separate lines is to make it a little more readable. All right. And I could end off this if statement here now. And this ends off the overall if for the clock logic here. Okay. That basically takes care of this counter process. So just to reiterate, the process is only governed by the clock signal. All right. If the current state is equal to north-south green or east-west green, that's here, or here, that's when I want to reset my counter. For every other state that I'm in, the other 6 states, that is when I would like the counter to be incremented. All right, so what's happening here is while this process increments this counter separately, this process, because the state transition process, because it's concurrent to that counter process, always has visibility to the value of the current count. All right, the reason why we don't need to say if count equal to 300,000 reset count to 0 is because this range takes care of that for us here. Okay, last thing that I need to write here now is my output process, and that just determines when my signals north, south, green, amber, red, east, west, green, amber, red are gonna go high. All right, so my output process here, it's a process, and of course the only time I'm gonna know which light to turn on is depending on the current state that I'm in. All right, so I have to look at what is the value of the current state, and let's see what's gonna happen here now. Okay, so the first thing you'd want to do in this process is to turn off the lights, and this ensures that every time the state changes, we don't have the lights randomly flickering or randomly on or anything like that. So north, south, green, north, south, amber, and these are not referring to states, okay? Note that these are referring to the outputs that I declared in the entity above here. Okay, north, south, green, north, south, amber, north, south, red, east, west, green, east, west, amber, and east, west, red. Right, then the next thing left for us to do is to determine the outputs based on the state that I'm in. And of course, I can use a case when statement for this. So, the case of when the current state is when I'm in north, south, green, what do I want to do? Well, of course, I'm going to turn on my green light, right? While this light is green, we know that the east-west light must be red. Okay? So we have to make sure that we put that logic in there. When I am in the east-west red to north-south red, or north-south red to east-west red, this is the case where both of those lights are going to be red, then I want to turn on both of my red lights. This is that 3-second phase. Right? We're assuming here, just put a comment at the top here, assume 0, assuming that 1 turns on light, 0 turns off light. Cool. When I'm in the east-west green state, that's when my east-west lights are going to be green, and at the same time my north-south red has to be on because my north-south lights have to be red. When I'm in the east-west red plus amber, well, that's when my east-west amber is going to be high, my east-west red is going to be high. But while those are red plus amber, the north-south lights are still red. We always have to make sure that we take care of the logic of the other set of lights. Okay, what's going to happen in my, let me see, we started with north-south green, then we went into north-south red plus red. We looked at north-south. Okay, let's look at north-south orange and east-west orange. Actually, let's take care of the orange states here now. When my system is in the north-south amber state, then my north-south amber light is going to be red. My north-south amber light is going to be on, and my east-west red light is still going to be on. When I'm in the east-west amber state, then my east-west amber is going to be on, and my north-south red is going to be on. Right? Just think of how the traffic light works so that you could figure out the logic for this stuff here. Okay. Let's see, we did east-west red plus amber. Let's now do north-south red plus amber. Right, and that is when my north-south amber light is going to be high. My north-south red light is going to be high. And my east-west red has to be high in that state. Okay, and let's see, 1, 2, 3, 4, 5, 6, 7, 4. 1 state, 2 states, 3 states, 4, 5, 6, 7, my 8 states, right? 1, 2, 3, 4, 5, 6, 7, 8 states. So we have when north, south, or east, west is green, then the corresponding lights need to be green and red accordingly. When I'm in the red state, both of my lights are going to be red. When I'm in east-west red plus amber, east-west red and amber have to be green, high, because it signifies that I'm going to go to the green. And because I'm going to be turning green, my north-south red has to be high. When I'm in north-south amber or east-west amber, that implies that I'm going from green to amber to red, which means that north-south amber is going to be high and east-west red is going to be high. Likewise, east-west amber is going to be high when I'm in that state, and north-south red is going to be high. And then when I'm in the north-south red plus amber, it's kind of like east-west red plus amber again, where both the red and amber lights of that intersection or of the north-south direction are going to be high, but my east-west lights have to be red because north-south is going to turn green soon. All right, so that takes care of that there. I can end off my case statement, and of course I ended my process already, and that's basically it for the architecture. It's always important to note that because we have these multiple processes inside here, that they are running concurrent with respect to one another. In other words, while this process, the state transition process, is determining the next state that I'm going to, it is reliant upon the value of the counter. The value of the counter is being determined in the counter process based on the change of the next state logic inside here. That is going to determine what state I'm going to change to on every rising clock edge in my state changer process. And of course, based on the current state that I'm in, which is set by this state changer process, it is going to determine the output of my system based on the traffic lights. Right? And that takes care of that for the VHDL architecture for this piece of code. All right, now I know it seems like a lot and we took quite a bit of time doing it, but that's because we're going through this in much detail. Once you get accustomed to this stuff and you see these questions coming in the exam, it should take no more than an hour, as long as we remember the different parts of the architecture. We're always going to be writing code for a finite state machine. And when we're writing code for a finite state machine, one thing to note is that we're always going to have a state transition process, and a next state logic process, and a state transition process. If we are using timers or counters, if we are using timers, we need to have a counting process, which is going to do some sort of frequency division for us under the hood. And we are also going to have always an output process. So those are typically the 4 processes that we're always going to need in a question like this. All right. Last thing I'd like to do is just to compile the code, make sure everything is correct. So we have some minor errors here. I probably left out some. So let's see. Okay, missing semicolon here. Right, okay, so I think this could be the problem here. When I'm in the east-west state, or I'm in the red. Let me see if this is going to help anything. Can't determine definition of operator or. Going to be this. Alright, so to make life easy, let's just split this up, right? Because we're probably getting an error there. So I'm just going to have separate statements for when I'm in east-west red and when I'm in north-south to east-west red. Alright, in both of those cases, my outputs are going to be, my red lights are going to be on. Alright, and the code is compiling there. So what you do now in a case like this is if you are writing code like this and you are required to upload those code files for examination, you would have to navigate to the folder that you created the project in, which is why I always specify when we're creating a project, always create a new folder to hold all of that code in. All right. Now I named my folder Past Paper 2019, and I created one VHDL file called trafficlights.vhd. Note that it's always this file, this .vhd extension file, that you're just simply going to copy and probably paste into a flash drive or something. So let's see how we can do that. We can copy the file, right? And we can probably create a new folder. Let's name it something like After Yourself plus your SBCS ID, right? Paste it in there. Then you are going to zip this folder by right-clicking on the file, send to compressed zipped folder, and that actually creates a zipped file of the folder for us, right? And this zipped file is what we are going to either upload to Moodle, depending on the format of the exam, or to a flash drive. Okay. All right. So that basically takes care of the first case study for questions 5 and 6, or the first case study for section B, which is the traffic light control question. I will be creating a separate video for the VGA controller to kind of break up the videos so that it doesn't get too tedious. All right, so until the next video, we will look at the other question. All right, thank you.